I know this is even earlier since our last class is 24th. You only have 4 days.
24 we have ENM exam.
28.
28, yeah.
ENM.
Yeah.
So you want to move to this. This is Monday. This is Friday, right?
Yeah.
So you have EMM on Friday.
ENM exam, yeah.
Okay, so now let's just move to Mondays, okay? May 1st. That is Monday. This is Wednesday. Which time you prefer? Morning.
24th to Monday.
Oh, sorry, yeah, Monday. That's the last class. Yes.
Time.
Hey, waiting for you. Yeah, final exam. That's because I remember after that maybe 2 days or 1 day or 2 days I have to submit this your final score. So that is maybe the last possibility, the latest. May 1st is okay. No any other exam, right? And you prefer morning or start from when?
Did a 1 p.m.
1 p.m.
Your class time. I think we did it 1 p.m. last time.
Okay.
Something like that.
1 p.m. All right. I am going to announce on the blackboard, and if you have anything, say, oh, I found I need some conflict that need to change, let me know.
Is Monday the 24th our last day of class?
Yes, that is last day class. I just delivered the final exam, take it home. So you just bring that to the home, and then you have almost 1 week, right, to work on the take it home. That is 50%. Then come to the in-class, that's another 50%. Chapter 8, 9, definitely. 10, it depends. Since this Monday we also miss 1 class. So I plan at least we have 2 or 3 classes for the chapter 10, but now we may only have 2. So let's see how much we can cover, and then we will cover in the class, in the final exam. Okay, now I will not wait, so let's start it. Continue discuss the spin object coupling, that we consider there's a spin electron move around this nucleus as an orbital, but also as spin itself, so that the interaction or coupling between those two, we have another contribution to this. So now let's remember this spin orbital coupling. That is, into the lunar Hamiltonian, we have the zeroth order plus the SO, right? So where the SO is the term we derive, which is E squared over 2 MEC squared 1 over RQ, and this is the inner product L is S orbital, and the mountain is a spin, right? Remember this. Then, so that if we add this come to here, we know this term we can write in terms of J squared, L squared, and S squared, right? So this one is E naught. Okay, there's a half on here, so it is a 4 and E C squared and J squared minus J squared. I think we end of this last class. So now we are going to do this contribution here. Right, this contribution, so since we know the energy En is from zeroth order plus the contribution from this one, right? So here, this is a hydrogen, so this is a digenerate. So we have treat this one and this in principle is a degenerate perturbation, right? Perturbation. Here. And in principle, that means we have to solve this determinant SO alpha beta minus E SO delta alpha theta. So the determinant of this Slater, I mean this how many depend on alpha beta, this index of the degeneracy, right? Then in principle we solve this, so we can find this by solve this rule, right? And that is clear. So here, if you remember, this SO alpha beta is the matrix element of say zeroth order. If I'm going to use alpha, the index, and I'm going to extend this one. Right, so in principle it's to this, but let's see in this case. This case a little easier is like first we analyze. First zeroth order, right? So H naught and alpha equal to E and naught psi and alpha zeroth order, right? For hydrogen atom. So here, the degeneracy is n squared, right? For given n, we have n squared since L and M L. Then here, the alpha, okay, this really depends how to select. Let me do this way because this way there are two ways. So here, the psi n alpha either is we select quantum number n, L, S, M, L, M, S. Or, if you remember, we discussed the addition coupling in the chapter 7, we can select J1, J2, J1Z, J2Z. Remember that set. Or J is J equal to J1 plus J2, so that is L, S is J1, J2, and J and MJ. In this case, sorry. Alpha is, so the index N, L, S, J, M, J. Here, this one is we use H naught commute with L square, S square, LZ, SZ. Is a mutually commute. So the quantum number N, L, S, N, L, N, S, this good quantum number. Good quantum numbers. Right? So good means we can use those quantum numbers to characterize these quantum states, and since they are commute, so those are they have joint eigenstates with this one, right? But here, this one is H naught J squared, L squared, and S squared, and JZ. They are mutually commute. Each other. So the quantum number in this case, N, is a radial part, right? N and J, L, S, and MJ. They are good quantum number. Good. Numbers. So easy. So we can have select two sets. Either this set mutually commute, so the joint eigenstate is this one, or this one, since H0 commute with those two sets. But now the question is, we want to calculate the contribution from the spin orbital coupling, which is depend on J square, L square, and S square. So because, remember J square with LZ do not commute, right? And also J square, SZ do not commute. So this term is, so what happens is, if we use the first one, therefore this, use N, L, S, M, L, M, S, the matrix element of this spin orbital is not diagonal. Prime. Okay, N same, but is not diagonal. Means what? When you solve this matrix, you have not diagonal, so you have off diagonal term. You have to solve it mathematically. I mean, that is make your contribute. It's not easy. However, but this one, N, L prime, S prime, J prime, M, J prime, with SO, because it's commute, N, L, S, J, M, J is diagonal. It is B give us the term. I'm going to use this SO contribution, delta L, L prime, delta S, S prime, delta J, J prime, delta M, J, M, J prime. What that means? So if you solve this one, it's only diagonal, off diagonal is 0, so that means the immediate diagonal term is this one, right? So when you want to solve this one, you first consider if this case, this contribution, this is a perturbation term. If it is, we can find the joint eigenstates such that they all join commute each other. So this joint eigenstates also the eigenstates of the whole Hamiltonian, or eigenstate not only H0 but also this one. Then you just direct to the calculate this one enough, right? You don't need, because this is what we need. That makes sense? Okay, if you follow me, then that is why they come to here. So immediately we have, so let me select this one. Okay, so what we are going to select, we are going to select the good side of the joint eigenstates or good quantum number such that this perturbation term is diagonal. So we select this one, N, L, S, G, M, G. Right, that's all. Okay. So this one, so the energy from this spin orbital coupling is nothing but now to save time, right? So we just use Dirac notation. So that just use quantum number. Okay. So that is N, L, S, J, M, J. Apply this one. N, L, S, J, M, J. Then we can immediately obtain this energy correction from this spin orbital coupling. This correction is, I think we also obtained, but continue. So here, N, L, S, J, M, J. Now this spin orbital coupling is here. We have a constant 4 MEC square, and then okay, this 1 over R cube here, right? So then 1 over R cube, then J square minus L square minus S square. N, L, S, J, and J. So that is our job. And here, let's see. this one is a radial part, right? So radial part only depend on N and L, right? Those are the products. So that means, let me take this constant outside for M E C square N L 1 over R Q N L. And here, this is for okay, let me do this, otherwise we may jump. So now let's see this one. If I still use here, keep going here. 1 over R cube. Now these are the eigenstates of G square, L square, and S square. So we immediately got this, that is H bar. So, yeah. H bar squared, right? And inside J plus 1 minus L plus 1 minus S plus 1. And L, S, J, and J, right? Since that the eigenstates, each one, J square is H bar square, J, this one, right? This L square, that S square. So now you can see those are numbers. The only remaining is this one. And now this is only radial part. So, let me pick the constant H bar square E square. So here 4 MEC square. Now, since R only is radial part, it's only dependent on quantum number N and L, right? The other is spin part or angular part is orthogonal. So that is NL, if you agree, NL. Sorry, here. G plus 1 minus L plus 1 minus S plus 1. It is here. Because R does not depend on the spin part and the total, right? Just for giving L. This one, that's equation from the chapter 6. Okay, go to chapter 6, equation 684. We have the result, so now I'm going to write the final. Okay, final is, this is a constant here, still keep it. Square. Okay, now I keep this, this is J plus 1 minus L plus 1. Now S is half, right? So half plus 1 is 3/2. And then it's a half, multiply half, so that's 3/4, right? So that is, since in this case. And then now I'm going to write this one. This one is 2 over N to the Q, L plus 1, and 2L plus 1, A now, Q. This is a come from Q. And now I'm going to organize here. Space. Okay. To save time, I just get the final, and I'm going to. I think this is just easier for you if you know each definition. So the G plus 1 minus L plus 1 minus 3 over 4 divided by L plus 1, 2L plus 1. Here we introduce, if you remember first, E and naught is minus E square over 2A naught N square. And alpha, which we introduce, is a new parameter, which we call this fine constant, structure constant, alpha here, right? Alpha. Alpha is H bar, MEC A naught, and if you substitute A naught, it is multiplied by E square over H bar C. since A naught, just remind you, right, this is chapter 6, you already know this constant. Okay, so that alpha we code is a fine structure constant. And it's dimensionless. It's kind of. Okay, so from here to here, you just if you know the definition, each you can find out. Now you can see here. Once we nothing to be introduced, a new parameter we call this fine structure constant. That gives the level how much the contribution of this spin orbital coupling compare with and perturbation H naught. So that is why we say that is perturbation. Now you can see here. Let's first so total energy correction here. Now the total correction, let me first, N naught plus ESO 1, right? So that is minus EN naught here, and then that one is EN naught over 4 over N. Yes, over N. Square. G plus 1 minus L plus 1 minus 3 over 4, L plus 1, 2L plus 1. So here, the index now depends on L and G, right? So now here, L and G. You see that is we split or the shift the degeneracy here. This degeneracy is N squared, right? So that is a left shift or left state degeneracy. Reduce the degeneracy. Now let's first the contribution. How much is the ratio of E, the contribution from spin orbital coupling to the initial and perturbation term. That is, since we have this one, right? That is alpha squared over N. Okay, and inside is those contribution. And you can see the dominate is by the alpha squared L plus 1 to L plus 1. That's proportional to alpha squared. And we know alpha is a constant number. It's about 1 over 130. So that is 37. That is 10 to the minus 2. So that is 10 to the minus 4. Yes, it is small, right? So that means in chapter 6, at the beginning we consider hygiene item. We ignore this contribution due to the spin and orbital coupling. And now that is the fundamental or unperturbation term. Yes, that dominates energy level with high degeneracy, the spherical symmetry of the potential. And now if we consider switch on this spin orbital coupling, there's a contribution, but this contribution at this level. Okay. And now you can see here this energy now is depend not only on N but also on G and L, right? So for example, how much we can, it will not 100% of lefty since we also have no any ML or MG, right? So that is partially left degeneracy. For example, if N equal to 2, then we know L can have 2 values, right? Then G is L plus minus R. So how many? Then we have E, okay, E here, right? N, L, G, right? So E, N is 2, L equal to 0. When L equal to 0, G is half, right? This one. And the second one is N equal to L to 1, J is 1 minus half, right? J is 1 minus half this one, so it's half, it's L is 1, and another one is 2, 1, 3 half. When L to 1, J plus half, so that is 1 plus half. So we have 3 levels. Of course, when n equal to 2, we have 8, the degeneracy is 8. But after we consider the contribution from spin orbital coupling, then this 8 degeneracy is split into 3. So there still have a partially degenerate, but at least it's reduced in the degeneracy since this lower the symmetry, right? That is one contribution from the spin orbital coupling. Now, it is interesting we found that if we want to consider the contribution from spin orbital coupling, which is in this order, there's another effect we have considered, that is a relativistic contribution. So, second one, contribution. Let's see, this contribution, why we have considered this, because they are in the same level. So here, let's first consider the contribution from there. That is the kinetic energy, since we know the electron move very fast, right? So because the kinetic energy operator is in this relativistic, this format is this one, right? P squared, the linear momentum, and C is constant, me square C to the 4th minus this one, right? That is the kinetic energy operator when we consider the relative level here. So this one we can expand in terms of P squared. This one. The rest, and then we have a non-rest contribution here in the Taylor extension. So here I just to save time and let's try to see this one. Approximately is this term, and when P squared is 0, right? That is the 0th order correction. When P squared equal to 0, plus first order 1 factorial, the first order derivative is this one, right? And multiply this difference is P squared. Then if we up to the second order, okay, here I need, this is a variable, so that is square, do this. One of the homework I assigned is some of this, deal with this, the relativistic correction. To the 4th power and plus highest. So when you do that, you will very easy, because here this P squared equal to the resistor, right? Square root of M squared, ME squared C to the 4th power, that is ME C squared. And second one is nothing but half of this kinetic energy in the non-relativistic case. So you will see, you just do the derivative. And then the third term is a negative 1/8 P to the 4th power divided by MEQ C squared. Okay, plus high order. But now we are going to just, since we consider this P squared is small compared with this order, so we have up to this, just up to this second, this is the 4th power. So we have this kinetic, then this one is equal to, you see here, this is this term, right? So subtract this equal to this non-relativistic contribution, and this one is associated with relativistic contribution here. That is kinetic energy. Then now we consider the Hamiltonian. If we consider, Hamiltonians is kinetic energy plus potential energy, right? That is this term plus minus this E. And potential is minus E, the Coulomb potential. That is Hamiltonian for the hedging atom if we consider the relativistic contribution on the kinetic energy operator. These two are H naught, right? And then this term is, I'm going to use HR, which is contribution from relativistic. So now let's see this contribution or this kind of perturbation, how much it is affect this hydrogen atom, and compare with the spin orbital coupling. Are they in the same order or not, right? So now here, the correction energy for any given n quantum number, we know it has the zeroth order, which has the n squared degeneracy plus the r, which I'm going to use this index here, right? So we're going to see this one. And again, before we do that, usually we have used the degenerate perturbation theory to solve this Slater or determinant, and by this matrix with the n squared degeneracy in general. But now, if this one, the operator of this commute with this one, so we can use the joint eigenstates of this one. So now let's see. Because here, that is the p to the fourth power, right? The linear momentum always commute with angular momentum, right? Because it does not independent with J square, L square, L square. That is very easy because this is just the momentum part. Does not depend on this angle, so that mutually commute. That is the good topic each time. We first look whether they are commute each other, then we try to find if there is a joint eigenstate. Mutually commute. So this eigenstates, joint eigenstates which we use, okay, I use it. The quantum number n, l, s, total j, because it's a total j, right? And mj is a joint eigenstate. Joint eigenstates of total Hamiltonian. If it is joint eigenstate of total Hamiltonian, so we just directly apply the operator to these states, we can obtain this one, right? So very easily, the contribution from this relativistic is just this n, l, s, j, m, j, and operator hr, n, l, s, j, m, j. That is directly we can just, and this became very simple since this is eigenstates of this, so we just try to find the eigenvalue. So that is equal to n, l, s, j, m, j. Now let me sum. Oh, I didn't give this. Okay, this one is hr, right? So hr is minus. Just remember here we have a minus p to the fourth power, and the value 8 m e q c squared. Okay. So these are constant I take to outside minus 1 over 8 MEQC squared. So the remaining part is just try to find this p to the fourth power under or within this sandwich with this eigenstates. That is how to do. How to do that? Anyone give me think about how, what can we do this? We know that is okay. that is not the Hamiltonian itself, right? So how to obtain this one? Let's consider this. H naught is half p squared minus E over R, right? It's here, H naught, right? So from here, I know the p squared is H naught plus E over R multiplied to ME, right? Okay, so this p squared and the p to the fourth power just squared, right? So ER is minus 1 over 8, and okay, let's just consider first. Consider this one, right? So this one is NLSJMJ p to the fourth power, NLSJMJ is equal to, now I'm going to, so that is NLSJMJ H naught plus E over R squared. NLSJMJ. So I'm going to, because it's a square, right? We need to extend it, so now I keep coming here, NLSJMJ. That is H naught square, because H naught come in itself, so we can take square. And second term is H naught E over R. Third term is E over R H naught, and the last one is E square R square, right? That is you square, expand this square of this. So we have 4 terms. Then now we can do, because we know H naught, this is the eigenstates of H naught, so that is E naught, right? So we can obtain this one is also H naught, apply this or apply this, because it's a Hermitian. So here, let me write down. So H naught square, so that is E in, let's see here, that's a square, okay, square, the first term, right? Second term, this apply this graph is also, let's put it this way, E and naught, and here I keep here, and this one is E over R. H naught applied cat is E and naught, and the last one I keep here. From here to here, the reason why we try to replace this p to the fourth power, since we do not know when p apply this how much. So but we know it is actually H naught, so we have replaced this one. And do this one from chapter 6, we have the result, right? So now let's here.
Dr. Yu,
Yes.
is this E squared over R supposed to be E over R?
Oh.
Or are the
no,
other ones E squared?
This one is square. Which one? Your question is what?
Yeah, so H naught right there, P squared over 2M
Yeah, this one plus
on the
this
right
one.
side, E.
Oh, yeah, you're right. That's right here. Yes, you're right. So I missed the square here. That is because this the interaction between the electron and the proton, so we have a charge. Yes. First part, right? Okay. So these two, those are constants we can combine with factor 2. I took this outside, but I keep this one because this is the integral between these two states, right? So that is, okay. Oh, yeah, okay, right. 2, I think I miss also here, there's a 2 dash. Right? I forgot. This is a p square. We have a 2me, but the 2me square. So up here. So now we have 2ME, and now, okay, let's see here. So the inside here, because you see this is a constant, so this orthogonal, right? Also normalized, so that is inside here. The first one is E and naught square. Second one, this one is twice of E and naught E square, and then this, and the remaining is 1 and L, 1 over R and L. Since the other, this R does not depend on the other angular momentum, so that the normalized, right? So only this term, and this one is E to the fourth power and L. Did I? Yeah. Now, the remaining is this one. Again, you go to chapter 6. So we have a chapter 6 equation, equations 6, 2, 6, 2, 31. And equation 6, 2, 20. For these two. So I'm going to finally give the result because this integral finally is numbers. Now the number is, let me first write down the intermediate step, and E. Now I'm going to take this E naught square outside. This is a 1, right? And this one kind of 1, so we have to divide it by 2 E square over. And here, this one is N square, the last one. Then I have no E square here, so I have a denominator is E N naught square. And this one we have the denominator is 2L plus 1 N naught square and N square. And here we have E to the fourth power, denominator have factor 2. Okay, now if you final, you just organize this, you will see that his final is 2ME E and naught square and 8N over 2L plus 1 minus 3. Finally, you will see this contribution only depend on N for given N, but then different L will have a different value, which is lefted, this degeneracy. Not finished, since we are going to introduce alpha, right? So because alpha, this term has also alpha, so now we give you final is, this is a p to the fourth power. Now finally we are going to go into this one. So now, so ER is, we have this minus this one. Minus 1 over 8 is minus 1 over 8, and Q C to C square, and multiply this one. So we have 2M E and naught square, and 8 and 2L plus 1 minus 3. Finally, we are going to introduce alpha, so that is negative E and energy N to square and R square over 4, 8 and 2L plus 1 minus 3. That is contribution from the takes the contribution, and you will see it also in order of alpha square. So that means the contribution compare with the zeroth order from this relativistic, that is approximately alpha squared, which is 10 to the minus 4 order. So yes, if we consider spin orbital, we have also considered this contribution was also considered from this relativistic contribution. So that means that this, so the Hamiltonian here, we have perturbation term. Then if we add the contributions from spin orbital coupling, we have also cannot ignore the contribution from the relativistic. That is in general. So because they are in the same order. Okay, because this, so now we say this contribution from both, we are going to say that is a fine structure, HFS. So here the definition HFS is just contribution from these two, spin orbital coupling plus the relativistic contribution. So this is a fine structure. That we call, so when you read this paper or this some of the concept about this fine structure of hydrogen, what does it mean? That means the contribution from this spin orbital coupling, we will consider spin and the electron also has an orbital, so that contribution and relativistic. This is a fine structure. Now we come together, let's see, energy correct from the fine structure speed, energy from correction from the spin orbital and plus, right? So this fine structure energy is SO plus ER. Then I already have SO, right? So we just add together, which is equal to the first spin orbital coupling is this term. Just divide 4. And then this, the relativistic is negative, right? So here, this term. N to the alpha squared, 4, 8N, 2L plus 1 minus 3. So these two contributions. And you will see this depend on L and J. For given N, we have a different value of L, then for given L, we will have a different value of J. Now, you will see we have, we will find that even though this looks as a complicated or large term here, but when we consider in terms of J, you will see it is actually, it can reduce to a little bit simple than this one, right? So let's consider. Since J is equal to plus minus L plus minus half, right? Right. So L is J minus plus half, right? Okay. So now let's consider first for J is L minus half, then L is J plus half. In this case, let's see this the correction from fine structure, the energy correction. And let's give you the first step, and then the remaining part we will skip to save time, right? So that is J plus 1, now L. L here is minus J minus, okay, sorry. Consider first, so this minus. Is this L is J plus half, right? And J plus half plus 1 minus 3, 4. And the denominator, J is all this, this is, okay, we have that. Let's take n inside. Since we have one is n, another n squared, so that's n here. L is J minus J is plus n is minus. j minus half, j minus half plus 1, 2 j minus half plus 1, this term, and then the next one minus e n naught alpha square, okay, and inside here, I move this 4n square inside. So it's 8n, 4n square, and L is 2j minus half plus 1 and minus 3. Oh, here, we have 4n square. So then they combine, you have organized, you will see finally, just give you final result. Finally, it is very simple. It is zeroth order and 4n square alpha square 3 minus 4n j plus 1. That is final expression. And you can see this is only for j. For given j, we will have one value. Then we have n. For j, it depends on the L. So this case is for j equal to L plus half. Since j have two values for given L, right? Now let's consider another case for given L. J has L minus half. What is expression for this fine structure correction? And you will see they are equal. They are same. So now let's see. Second one. Second for j equal to L minus half. So L is j plus half. You just substitute those into the L into the formula. Then you will see here. So the fine structure, the contribution is E and naught alpha cube, and then the inside is j plus 1 minus L. L is j plus half, right? J plus half plus 1 minus 3 over 4. And here we have n inside, right? So that is n and L, which is j plus half, j plus half plus 1, and 2 multiplied j plus half plus 1. Right, that is the first term. And minus 1 over 4 n squared. This inside is 8n. Then the 2 j plus half plus 1 minus 3. Then we organize all the together, so finally you will find this is finally same thing. Okay. 4n squared, squared, and inside 3 minus 4n over j plus half. Right? Same thing here. So that means whatever j is equal to L plus half or minus half, it is the same formula. The only thing here, you just change j. So finally, let me just combine together. We have this fine structure contribution. It is the final energy, the nth level. Now it is G actually implied with L, so now it is dependent on G for given n, zeroth order plus the fine structure contribution, and that is zeroth order. Here we have zeroth order, but we use absolute value, meaning this is a positive, right? So if we use this is a negative, so when we take outside, it's 1 minus, right? We have a minus sign. 1 minus. Just changing position. change position, so have a negative sign, right? So that is here. I take off this E naught, so we have alpha square. We got this plus. So also now inside that just change 4n g plus pi minus 1. And the g has two values. So for given n, of course, for given n, we have a different, for n, we have a L equal to 0, 1 until n minus 1. Then for given L, G has L plus minus R. So you can see, that is implied, that means here, when we consider n equal to 2, for example, then you consider L equal to 0 case, we have a G plus minus. Then L equal to 1, we have a G plus minus. So there are several correction or this negative energy level. Let's try to go down. Okay, now we know what is a fine structure. There are also another contribution is from this another code is this is a hyperfine. This is a fine structure contribution, right? Hyperfine contribution is not, in addition to those, we know each spin associated with electron and nuclear, they also has interaction. That is the coupling of two, addition to spin angular momentum. That contribution will adjust or contribute to this energy level. So we call that is hyperfine structure that we will not discuss. We more discuss is another issue which is very important, is because it's the anomalous Zeeman effect. We have discussed Zeeman effect in chapter 6. So in chapter 6, we consider only the contribution, only the contribution from the orbital magnetic dipole moment, right? So suppose we have the Zeeman effect is we have an internal, this external field. So if we have this orbital, this magnetic dipole moment due to the orbital angular momentum, the interaction between this is a normal Zeeman effect. In chapter 4 and chapter 6 we discussed. In that case, we know that the splitting is odd number. Splitting is dependent on this m value, right? 2L plus 1 m minus. So for given L, then we switch on the Mach field, we found out this speed from 1 to either 3, 5, 7. Why? Because for given L, we have odd number of ML. That depends on M. Now, if we add spin, suppose we have also spin here. Electron spin has a spin and also associated with spin, we have a spin magnetic dipole moment. So that interaction together, this together, we call that is anomalous. Anomalous Zeeman effect. Which is that the split this energy spectrum is very complicated. We need to see whether the field is strong or weak. So that is so what that means anomalous is we consider spin also. So because we consider spin so Hamiltonian, let's just consider we give this Z, which is a Zeeman effect. Now we have two contributions. One is from this orbital magnetic dipole moment, another is from spin magnetic dipole moment. So that is a new term. If we consider the spin contribution, then we have this. And now the first term, if you remember this, so that is number is E over 2 MECL in the product of the orbital angular momentum is a field, and plus the spin part is E over MEC as B. these two terms. Here, definition of this orbital Mach dipole moment is negative E orbital operator. And we see why this is the factor 2, but for spin, there's no such factor. And that is associated with this Landé factor. Okay, so if this, now we can continue. And just, so the contribution due to the interaction between this orbital and spin dipole moment with the external field, this is the external, right? External field. Then that is, I'm going to, so because this inner product is, assume that B is along the z-axis direction, right? So this is direct number E, 2, and C, I take all sides, so now here, this is the LZ, right? Okay, LZ plus 2SZ. Now here the E is here. That is the term. Now we are going to see how this contributes the energy, or how this energy level is needed by this effect. So to consider this effect, first we consider there are two cases, right? The contribution, the total Hamiltonian is, we consider the M-perturbation term and the fine structure, then this the contribution from the Z-band effect, anomalous Z-band effect. So that is the total. Since we know this level is in the alpha square, right? Now let's see this one. Now this one is dependent on external field, whether the field is strong or weak. So the contribution, this compared with this one, is really dependent on this one, right? So now we are going to discuss two cases. One is a strong field, another is a weak field. What happens, right? So let's consider if this the spin, the fine structure is much smaller than this contribution from this one, we call strong. Or strong field. Z-band effect. If this contribution fine structure is much stronger than this, we call it weak field. Z-band effect. So we are going to consider these two cases separately and see how this contribute, and how to consider this measure which one is strong, which one is weak. Let's look this one, because we know the S. Actually, the S. This one is only this part, because this is only dependent on the orbital, right? The contribution. And the fine structure, only the SO, this optical spin coupling is contributed with, associated with this orbital, right? So we are going to consider this, ignore this relativist contribution. That does not depend on this orbital. So we just consider this one. So let's look this one. SO is, if you remember, the SO we have this term, right? 2 n e square c square 1 over RQ L inner product S, right? And that I'm going to use W L inner product S. So here W is this term. That's called the constant. And this 1 over. So this is only the orbital part, but the remaining contributions from here. Then the Z-band effect, I'm going to rewrite this one is in terms of this both mu b, right? Is equal to mu b h bar mu z, z plus 2 s d. z plus 2 s d. So the ratio between this the contribution from the Zeeman effect and this spin optocoupling is proportional to the B mu B H bar, this one, right? This contribution, they are same order. So we just look this how to consider this is larger or small. So that is given. So if B, if this is larger than 1, that means this is stronger than this one. Right? So that means B much larger than that is W H bar over BB. That is strong. Here. That is strong here. But the B is much weak in this value. So how to judge whether it is large or small? You're going to look those values. Then it is weak. Okay. Now let's first start consider strong, because strong is simple. So then we go to the weak. How this Zeeman effect can control. So first, for strong field, Zeeman effect. Okay. That means this is much larger than SO and of course the fine structure, right? Because fine structure is contributed by this spin optocoupling and this relative state. But relative state does not depend on orbital, so that means if this is the case, so the Hamiltonian is initially the 3 terms, but now is controlled by the only the unperturbed term plus the Zeeman contribution, since this term is much small. So now, and then here, this term has a LZ and SZ, so which joint eigenstates we are going to select? H naught L square S square LZ. SZ, right? They mutually commute. We have, since here we have LZ and SZ, but if you consider J square does not commute with these two. So that joint eigenstate with N, L, S, G, M, G, it is not joint eigenstate for this one. But this one commute, right? So what kind of joint eigenstates? N, L, S, M, L, and S. That is joint eigenstate. Does that make sense? Since you look at this LZ, HZ, this is only the LZ and SZ. Both that, like if you go to chapter 7, you know if this J square does not commute with J1Z, J2Z, right? This is J1Z, J2Z. So that joint eigenstates only this for, because this LZ commute with L square, right? SZ commute with S square, and of course they are not in the same space, so they mutually commute. H naught is radial part at L square, right? So that all joint. So this is a joint eigenstate. So that means now we're going to just consider contribution from here, because this is zeroth order, that is, we have just calculate this matrix element over this inner product between these states with this one. So that is are easily NLS and LNS and HZ and LS and LNS. And now we have, so this is a constant I take outside, E, E. Actually, I can use mu, so C. And now the N, L, S, and L, and S, L, Z, plus 2SD. N, L, S, and L, and S. So these are eigenstates of LZ and SZ, right? So we can immediately got these numbers, the eigenvalue. Inside, LZ is, take H bar outside, right? M, L, and 2 MS. That's all. So ML, we know that is plus minus L, plus minus L minus 1. And MS is plus minus half. So how the energy is split, it depends on which L value. Then we have the correct. So now the total energy now, En, I'm going to write down here since it's dependent on also ML, so now En, L will depend on L also, the L again implied with L, so now we just, even though not directed, so that M, L, and S is E and naught, which is N squared degeneracy, plus this one, right? Plus E, B, H bar over 2 M, E, C, M, L plus 2 M, S. Okay. How much you can split it, we can discuss for giving, for example, N equal to 2, L from 0 to 1. So M, L is 0 plus minus 1, right? Another value. And S is plus minus half. So you're going to substitute this, you will see how many levels. I just left it for yourself to see how much. I want to go to another one, is weak. For the weak field, right? Okay. Here, the Hamiltonian we have included fine structure, contribution, and this Zeeman effect. Since this weak is in this one, so this one definitely have to take into account. Then how that it is, now let's write down here, it is, okay, if you remember here, we have plus B 2 C L Z plus 2 S. Here, can we find the joint or eigenstate of this? So now, since we know this joint eigenstate for this one is let's do this one, because G square, okay, G square is LZ not equal to 0, and G square is SZ is not equal to 0. So N, L, S, G, M, L is the joint eigenstate of H naught and H phi structure. but not HZ, right? Since HZ has a LZ and SZ, then how to do that? But don't worry, even though it is not, but we can calculate this contribution from here by analyzing this one, and you will see that it's still diagonal term. So in first order perturbation. We have this, okay. We still can apply or use this eigenstates, dual eigenstate for H not the H fine structure as the basis or starting. Sorry, this is G. So if this one, now we to the first order, remember the first order perturbation, we have this, the contribution from Zeeman is just the sandwich between the states, right, of this, so that is N, L, S, J, M, J, and H, Z, N, L, S, J, M, J. Since you may ask, it is degenerate. Yeah, in the case, since here we have if you consider this one as a basic starting point, this is a kind of perturbation, right? So that one already have left some of the degeneracy. This together, add this together is joint X to this. So we use that joint X from here to see how much perturbation from here. That makes sense. That is this. The first order, remember this one. Okay, so now we are going to do this. Even though I want to speed up, it's not. Okay, let me, I think this one is some of the new information we need to discuss. Next Monday, I will continue to discuss this. So now, since the final exam, as I said, we have in class 1 day before the final, I need to submit this score, your final score. So I hope you can homework and can be turned in time. At least before 24th, that'd be nice. Or I still can give you after the in-class the exam, but in that time you have take a home exam, you need time. So think about to do that. I know this is takes time, so if at least you write down the correct formula, even though the integral, there's a lot of integral here, you can leave there, but give me the correct formula, the first integral, first step. And if you do not have time, the last one, but I need to know your correct expression. Okay, you have this one, right? Okay, yeah. So, do you finish your homework? Not yet? Okay. Have a variational principle. I'm not sure we can cover chapter 10. Variational principle is very also important, so I need to go that. Let's see. Okay.
어이 시간이야. 계속.
tomorrow?
because we can make sure that comes.
Yeah. Though that doesn't somehow my understanding is that